This brings us to a very important conclusion. Where unbalanced conditions exist, negative sequence voltage and current are produced by the fault, and these are superimposed upon the positive sequence quantities. Now let's move along and look at unbalanced faults involving ground. Here we see a phase to ground fault on phase A, and this is the resultant voltage phasor diagram showing conditions at the fault. The voltage on phase A becomes very small, depending upon the impedance of the fault. For simplicity, let's assume this to be 0. The phase voltages on lines B and C remain unchanged. The current in line A, that is IA, increases considerably to feed the fault. Note that we have drawn the current IA in phase with voltage VA. For simplicity, when using symmetrical components, the fault path is considered to be either pure resistance or pure inductance. Throughout this segment, we're assuming the fault path to consist of resistance only, and the current is therefore in phase with the voltage. The current in lines B and C is 0 in both cases, as system load is considered to be 0. Our phasor diagram shows that the system is completely unbalanced. The generator is still producing positive sequence voltages and currents, but at the fault, the positive sequence voltages fall to 2/3 of their pre-fault values. So once again, let's see how the positive sequence quantities are transposed into the unbalanced voltages and currents at the fault. Now remember our previous conclusion. Any unbalanced fault has negative sequence components acting on the positive sequence quantities. Now where a ground fault is present, we need to add yet another set of components. First, let's look at the voltages on line A. At the fault, VA equals 0. VA1 has been canceled out by the negative sequence voltage VA2 and the missing component, which we call VA0. Now that we have placed VA2, we can draw in the other two negative sequence voltages, that is VB2 and VC2. We know that these components are 120 degrees apart. They are equal in magnitude and rotate with the phase sequence ACB. Now let's look at the B phase components. We know that this phase voltage VB remains unchanged. Thus, the fault voltage VB is the sum of VB1, VB2, and the missing component VB0. Check in your workbook to verify that these phasors add to give VB. Similarly, with the C phase voltages. The phase voltage VC at the fault is obtained by adding VC1, VC2, and the missing component VC0. Now, another interesting factor becomes apparent. The V0 components in each of the phases are of identical magnitude and all are at the same phase angle. In fact, these voltage components have no sequence at all. So they are called zero sequence components. To review, to get each phase voltage at the fault, we add the three components together. For example, VA equals VA1 plus VA2 plus VA0. Now let's look at the currents. First, it is apparent that the current at the fault, IA, is about 3 times the magnitude of the positive sequence IA1. The difference, of course, is made up by the presence of 2 other sequence currents, IA2 and IA0, which are of the same magnitude and in the same direction. Thus, these phasors, IA1, IA2, and IA0, add up to give IA. Now that we have located IA2, we can draw in the other 2 negative sequence components, IB2 and IC2. We can also now add in the zero sequence current components, remembering the characteristic that they are always in the same angular direction. We know that the current IB is 0, and this must equal IB1 plus IB2 plus IB0. That is, the positive and negative sequence phasors IB1 and IB2 cancel out the zero sequence phasor IB0, and thus the total is 0. Similarly with line C, IC1 plus IC2 plus IC0 equals 0. This is what we should expect. There is a heavy flow of current in the grounded line, but there is zero current flowing in the uninvolved phases. Remember that we are assuming load to be 0. Again, we have seen that the sum of the positive, negative, and zero sequence components for each phase add up to give us the actual fault values. So we now come to another very important conclusion, and that is, where a ground fault exists, all three sets of symmetrical components are present. That is, positive sequence components, negative sequence components, and zero sequence components. And do note that within each set of components, the voltages and currents are of equal magnitude. The presence of these components provides a useful tool for detecting unbalanced conditions and ground faults. For protection, both zero sequence and negative sequence relays are installed. Typically, the negative sequence relay works by comparing voltage or current in all three phases and filtering out negative sequence components. The current coils are connected to CTs like this. The current flowing through each coil will be the sum of positive, negative, and zero sequence currents in that particular phase. Note that the zero sequence components, as they are all in phase, add together at this point and pass through the ground relay current coil. Now let's look at the VT connections. The primary and secondaries are Y-connected with grounded neutral. The secondary supplies potential containing positive, negative, and zero sequence components to the relay's negative sequence voltage coils. This enables the relay to detect the presence and magnitude of negative sequence voltages. Additionally, to detect zero sequence voltage, an auxiliary transformer can be connected like this. The primary is Y connected with the secondary in broken delta. The zero sequence voltage in each phase is summated and fed to the voltage coil of the ground relay. We'll be talking more about this in future tapes. The wide use of these relays serves to indicate a practical application of the study of symmetrical components, as well as their use as a mathematical tool in analyzing fault conditions. Our main objective at this point is to introduce the concept of symmetrical components and show how useful this method is in analyzing fault conditions. When faults do occur, the power system no longer operates with beautiful sine waves and balanced phasors. At any instant in time, we may have voltages and currents going in several directions, with magnitudes and phase angles being imposed upon each other. Breaking the quantities down into symmetrical components helps us visualize the conditions. In fact, any unbalanced system of currents and voltage can be represented by a combination of positive, negative, and zero sequence components. There are several basic rules we should remember in connection with this method. Only phase voltage components are used. The load current is considered to be 0, so that only fault current flows. Current in the uninvolved phases is taken as 0. The study is simplified if the phase angle of the fault path impedance is taken as 0. Only positive sequence voltages and currents are created in the generator. Under perfectly balanced operating conditions, only positive sequence quantities are present throughout the system. Negative sequence and zero sequence quantities are considered to be generated at the fault. With unbalanced conditions, negative sequence quantities exist as well as positive sequence. Where a ground fault exists, all three types of symmetrical components are present. That is, positive sequence, negative sequence, and zero sequence. The zero sequence quantities have the same phase angle in every phase at any instant in time. Summation of the positive sequence, negative sequence, and zero sequence quantities will show voltage and current conditions at the fault. We have included in your workbook this chart, which shows the positive, negative, and zero sequence components of current and voltage for the most common fault conditions. Please take your time to go carefully through each one of these items until you're satisfied that you understand the various combinations of positive, negative, and zero sequence components. Well, at this point, we all deserve a break and time to fix this material in our minds. So please switch off the tape and thoroughly review your workbooks.